Okay, so now we're in section 3.4 of Samuel's text, and we're going to talk about density curves. So if you recall from calculus, the total area under any curve is always equal to 1. So we're going to be finding intervals under areas of curves, and we are going to start with the normal curve and the formula for it, which is not anything you really need to know for this class, but it's good information. This is the Gaussian distribution, and there is your sigma, there is your mu for mean, and so the formula integrated between the bounds of a to b is 1 over the square root of 2 pi sigma, e raised to the negative, that's a negative, quantity x minus mu squared divided by 2 sigma squared dx. So since we have this formula, as long as we know what the mean and the standard deviation are, we can always integrate between two particular bounds. We're going to be using technology to do this, not calculus-based by hand methods. So the probability for a continuous variable equals the area under the density of the curve between those 2 points A and B. As an example, in 3.4.3 with blood glucose, if 42% of the population glucose levels are between 100 and 150 milligrams per deciliter, then the notation for this would be PR with the squiggly brackets. 100 is less than or equal to glucose level is less than or equal to 150. And it is equivalent to, rather than the inclusive, than the non-inclusive less than symbols, because at the inclusive we can't actually integrate. So that shows that the probability that it's between, the glucose levels are between 100 and 150 is 42%. Where we can use Y to be, sorry I missed this in my typing, the mean glucose levels. If we continue on, we're going to talk about not just the normal curve, but the standard normal curve. And the standard normal curve has a mean of 0 and a standard deviation of 1. And so typically all distributions go 1, 2, 3 to the right. Now it actually goes to infinity, but most of our information for all distributions are found between positive 3 and negative 3. In fact, one of the rules states that between 99.7% of all distributions are contained within negative 3 to positive 3 standard deviations under the standard normal curve. We call the standard normal curve the Z distribution, and so we can calculate Z scores. So we look at example 3.5.4 under the heights of men. We're going to let Y be capital Y, and random variables are usually done with capitals, but capital Y is the random variable for the height of a man chosen from a certain population. If we know that the probability is 46% chance that the mean height of males randomly selected is between 65.2 inches and 70.4 inches, then the notation for that is PR, probability, in the parentheses, 65.2 is less than or equal to Y is less than or equal to 70.4, and that is equal to 46%, or 0.46 as a decimal. If we show that on our curve, this is not a Z curve, this is a normal curve. Raw data gives us 65.2 to 70.4. The area between those is shaded in is 0.46. We can convert our Z scores for those raw data. We're going to do that later on in the class, so I will show you how to do Z conversions later. Here's an example, 3.5.5, the mean number of vertebrae for these particular fish. So when we have a distribution, we can take the percentages, change them to decimals, and multiply them by the counts. So we call this capital E for expected value, and mu Y is the same as expected value of Y. The expectation is also another form of the word mean. And we just multiply, again, it's like going through the probability tree diagram, the counts times the probability, plus each of the other counts times their probability. So it's the sums of the products. And so the mean number of expected vertebrae for these fish is 21.49. We could calculate the mean number of spots on a die when rolling a fair die. The count is 1, there's a 1/6 chance of that. The count is 2, 1/6 chance, and so on. If we take all the sums of all the products, we get to 3.5. So mu y is the 3.5, the mean number of spots when rolling a die. Variance, we won't really use this formula, but it's variance y is sigma squared y, and that is given by the capital sigma, the Greek letter sigma, meaning summation of each individual y value minus its mean quantity squared. And that's for the probability of some random variable y equaling some value y. And our standard deviation is simply the square root of sigma squared, and if you square root a squaring, you get sigma itself. So standard deviation notation is sigma y, and that would be the square root of this formula right here for variance. Those are not really things you'd need to know by memorizing or anything like that. You can always go back to look at this. I wanted to talk about a Punnett square because that's going to come into play quite often in probability. So that, many of you who have had some biology classes, you know about the Punnett square. Capital letters stand for dominant traits and lowercase stand for recessive traits. So there are 4 possible outcomes. If this is parent 1 and this is parent 2, the combination of them could be dominant, 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 recessive, in this case dominant recessive, or recessive recessive. So the probability of getting fully dominant is 0.25. The probability of having the combination of dominant recessive, which means you're a carrier, is 0.5 because there's 0.25 plus 0.25. And the probability of being fully recessive is also 0.25. And if we think about that, whenever you have 2 outcomes, that is a binomial outcome. Binomial meaning 2 outcomes. Bernoulli trials are essentially one binomial trial, meaning one trial where there are only 2 possible outcomes, 1 success and 1 failure. So if we toss a coin one time, we have a Bernoulli trial of 1 head and 1 tail. So going back to the dominant recessive, this is an example 3.6.3. If the probability that a child of 2 parents with a recessive albinism trait will be an albino is 1/4, 0.25, like we set up here. So and the notation for that, the probability that the child is albino is the probability that our random variable y is equal to y being the outcome albino is 1/4. And of course the probability of not having albino is the complement of that, which is 3/4. So if we answer the 2 questions, what is the probability that in a family of 2 children, both children are albinos? We show the notation. Well, in order to be an albino, it's 1/4. So for both of them to be albino, it's 1/4 squared, which is 1/16. What is the probability that one child is an albino and the other is not? So we have 2 options. Either the first is albino and the second is not, or the first is not and the second is albino. And if we look at those 2 products of probabilities, 1/4 times 3/4 plus 3/4 times 1/4, there's a 3/8 chance that one is albino and the other is not. Let's get into the binomial distribution formula in the next video. So I'm going to stop here, look for part 3 for the binomial distribution formula.